And then it says, well, hang on a second, these interesting features that we see in the member 4 hominins, maybe they actually are ancestral to maybe Homo.
What's up, you scholars of enlightenment? Fossils of early human ancestors in a cave in South Africa are 1 million years older than researchers previously thought, according to a recent study that gives insight into the history of humankind. Now, the study of fossils from the Fontaine caves, which yielded the near-complete skull of a cave woman nicknamed Mrs. Plez, and here's a nice little picture of that, were found to date back to 3.4 million to 3.6 million years. Now, the findings suggest that hominins in South Africa existed around the same time as others in East Africa, such as the renowned 3.2 million year old skeleton Lucy, which was discovered in 1974 in Ethiopia. Now, East Africa has long been considered as the more likely origin of the earliest hominins that eventually evolved into the Homo genus that we belong to. So this study reignites the debate on the origins of modern humans. Now, to help me dig into these findings and their deep and far-reaching implications, I welcome two fantastic special guests. Firstly, Professor Darryl Granger. Professor Granger, welcome to the show.
Thanks.
Professor Granger is a professor of Earth, Atmospheric and Planetary Sciences at Purdue University's College of Science, where he specializes in dating geologic deposits, including those in caves. Secondly, we welcome Professor Dominic Stratford. Dominic, how are you?
Hello, everybody.
Dominic is a research coordinator at the Fontaine caves in South Africa, and his work involves managing the excavation and processing of the finds at the site on a daily basis and implementing new research projects in the rich fossiliferous underground chambers. I like that word. So, who better to help me contextualize these latest incredible findings? So, first question. Prior to these findings, what was the accepted picture of human evolution on the continent of Africa in terms of geography and time, given the findings that we've had in the past and the fossils that we've seen so far? Maybe go to Dominic, I think maybe.
Dominic, you want to start with this one?
Okay, sure. So I think that one of the interesting things about this debate is that there's not much that has been sort of widely accepted, certainly within academia. There's always a huge amount of debate. Having said that, there are patterns that have emerged in the past sort of 50 years of research that suggest that places like Ethiopia, the Afar region of Ethiopia in particular, have yielded some of the earliest remains of fossil hominins. And then it gets a little bit more ambiguous as you get towards those times when you see the appearance potentially of the genus Homo, in which case then that can be in a couple of different places around Africa, between East Africa and then South Africa, where we also find some of these early hominins. Certainly the earliest hominins, so when we think about the earliest hominins, those are the species and genera that we think of as being the earliest representatives of the bipedal apes, so those are hominins. Those appear at about 7 million, and those have been discovered in sort of that sort of East Africa, the sort of Sahel region, and then through to places like Ethiopia. And then the earliest sort of most complete skeleton, things like Ardipithecus, and the two species of Ardipithecus also from that sort of northern East Africa region. And then it gets a little bit, as I said, it gets a little bit trickier as we get to that sort of around 3.5 to 2 million years, when we start to see the emergence of things that look a little bit more like what we think of as being early Homo.
Sure. So it might be helpful to back up a little bit and explain what we mean by hominin and hominid.
Please.
And traditionally, the hominids were considered to be the bipedal apes, like Dominic just said. More recently, when we look at genetics, people have realized that the apes are maybe more closely related than we thought before. And so we speak about hominins, which are the group that's most closely related to we humans, going back to, people debate on this, whether it goes back to the split with chimpanzees or to the split with other great apes, the gorillas and the orangutans. So when we speak of hominin, though, what we're referring to are basically the bipedal apes, since that split with chimpanzees, which would have happened somewhere around 7 million years ago.
So when we're talking about the closest relations there, we're obviously talking about dating fossils that we find as well. Are we also talking about the kind of structural makeup of the fossils that we find in terms of the kind of skull shapes and physical features as well?
Yeah. So you can tell a lot from the skulls. You can tell a lot from the teeth. You can tell a lot from, if you have the postcranial, the rest of the skeleton, and the feet in particular, and the pelvis will tell you a lot about how these animals got around on the landscape.
So
you want to, Dominic?
Dominic, please.
I think it's worth mentioning that as we're pushing back to that sort of 7 million year ago time period, and when we're talking about what we consider to be the last common ancestor between chimpanzees and ourselves and the ancestors of us, it's important to remember that chimpanzees have also been through 7 million years of evolution. And so it's not necessarily that we're looking for something 7 million years ago that looks like a chimp.
Yeah.
And so it gets trickier and trickier then to really differentiate between the fossil of a chimp or the fossil of the apes and the fossils of the earliest hominins. And that's quite tough.
Yeah,
absolutely. And they've evolved as much as we have since then.
It makes sense that it would be quite a kind of soft cutoff rather than a hard, easy to differentiate line. Why is it so vital for people who are watching that we correctly date the fossils of our ancestors? Is it so that we can get an idea of how we've evolved, where we came from, how we interacted with these ecosystems in the past? Why is it so important to get these dates correct? Dominic, I'll come to you first.
Well, to be honest, it provides us a sort of a calibration for us to be able to understand how evolution has worked, and then where those kinds of changes, and certainly when we look at the external morphology, so what we look like, then it's the evolution of those traits, those things like bipedalism, things like when we were using trees more or less. Those kinds of calibrations in terms of the chronology and when those things happened are really important for us to be able to contextualize those changes and then put those changes within both an environmental context, so what was going on within the environment, because there are large changes that are happening, and then smaller, more nuanced changes that are happening on any landscape at any point in time. And then, of course, as you mentioned, it's about trying to figure out where those changes were happening and when those changes are happening in relation to the other animals that were on the landscape as well. If we're thinking about evolutionary pressures, then it comes down to things like predation and also things like environment. And so understanding the balances and the payoffs of those different things is pretty important for us to understand when those things happened.
Makes sense. Daryl, anything to add on that front?
No, I think that's great. You find fossils, across Africa. It's really important to be able to place them in relationship to each other. So in East Africa, there's a really nice stratigraphic record. It's extremely well dated, and they're able to place these fossils in context with one another. When you go to other parts of Africa that are less well dated, we need to be able to figure out where they insert into the timeline and where they may be related geographically as well as temporally.
I guess we also have and this is a naive question from myself, but I guess we also have a problem with sampling as well. We don't get every single period that we want to get. We have a snapshot here, a snapshot here, a snapshot here, which we want to relate. Is there a need to find more fossils potentially from between East and South Africa and get more of a wider picture?
Yes, there's a very biased record. East Africa is in a rift, a tectonic rift, where the continent is spreading apart, and there are lots of lakes, and there are places for sediment to accumulate. And so you have continuous or semi-continuous sedimentary records where the fossils and other sediments are preserved. Other parts of Africa don't have this. If you don't have piles of sediment, it's really hard to preserve those fossils so that you can find them later. And South Africa is lucky in that there are caves. And so the fossils are preserved when they fell into caves. But in much of the rest of Africa, there's just not the geologic setting that's amenable to fossil preservation. You may have tropical weathering in parts of Africa as well that will help to destroy those fossils.
That makes sense. So that's a beautiful segue as well. Thank you, Daryl, because you're both very familiar with the Fontaine caves in South Africa, known as the Cradle of Humanity. Got some nice pictures of yourselves as well. Known as the Cradle of Humanity and designated a UNESCO World Heritage Site. Could you, Dominic, tell us a little bit about the site and its history and why it's such a treasure trove for understanding the story and the evolution of humankind? Why are we so interested in this site that Daryl flagged up there?
Sure, yeah. So Daryl introduced the sort of the context of the caves around the Cradle of Humankind really nicely, in that it provides us an alternative sort of catchment system for sediments and bones and stone tools that's different to the large rift valley that we see stretching essentially from Mozambique all the way up to the Horn of Africa. So in South Africa, we have a few exposures of a rock called dolomitic limestone, and that rock is soluble. So essentially what happens is groundwater will dissolve out large cavities underground. And at some point in time, those cavities then open to the landscape surface, and then you get the opportunity for things to fall in or sediments to wash in, and gravity driven just gradually accumulate inside the cave systems. And once they're in there, they're in there. So there is some sort of processes that go on underground that can sort of jumble them up a little bit, but essentially it's a bit of a fossil and a bit of a sediment trap. And that's fantastic. So it provides us these little keyhole sites around the landscape where different caves have opened at slightly different times, and different caves have closed at slightly different times. And those provide us basically these little snapshots, these little time capsules underground. And it's a very useful picture that you've got on at the moment, because it sort of introduces a little bit of the history of the Fontaine caves as well, and the caves of the Cradle of Humankind, in that essentially the earliest discoveries and all of the major discoveries of fossil hominins in the Cradle of Humankind have come about through mining activity. And sort of between 1890s and sort of early 1940s, large quantities of mining were being conducted in the Cradle of Humankind area. And what they were doing is they were dynamiting and blasting out the speleothem. That's the stalagmites and the stalactites that are so pretty, so beautiful on this image that we have up. The reason why they were blasting them is to take that speleothem, those stalagmites and stalactites, the calcium carbonate, and then you would take them to the Johannesburg gold mines, and they would use them for creating cement. So it was an industrial exploitation of the caves that was first responsible for sort of both exposing some of these very old deposits underground, but also in extracting some of these fossiliferous deposits and dumping them on the landscape, where the major discoveries were first made by people like Raymond Dart in 1924 of the Taung child. That's the first sort of hominin from southern Africa, and then later on by Robert Broom in 1936 at the Fontaine cave system. And that really did inspire the next 80 years of research at that site in particular. But as we know now, where we find dolomites and we find caves, there is a chance and an opportunity to find these ancient deposits underground.
That's amazing. I didn't know. So there's a little bit of natural weathering and also human activity that's helped us find these amazing findings. So that's a nice little history of the Fontaine caves there. Fossils from member 4 mentioned in the paper, a particular focus of the recent analysis that you were both involved with. Daryl, can you give us a little bit of information about what member 4 is? Maybe I've got a kind of diagram here. We've got this BH4. Maybe you can give us a little bit more information about what it is and what was found there.
So first of all, let me back up and say what these members are. So Fontaine has been filled up with sediment from the bottom up to the top. As these different cavities would open to the surface, you would have rocks and bones fall into the cave and tumble down. The lowest deposits are members 1 and 2, and then as you go higher up into the cave, the numbers get smaller. So members 1, or get larger rather. Members 1, 2, and 3 are exposed inside the cave at some deeper levels, and then members 4, 5, and 6 are found at the surface excavations where they blasted out and then later excavated the fossils. So the Australopithecines have been mostly recovered from member 4. This is a richly fossiliferous talus cone that accumulated in the cave, probably at the bottom of a shaft that went up to the surface. So the rocks would fall down the shaft and then tumble down into the cave. And you can kind of see that on the image by those slanted lines. Those represent the accumulation of sediment in layers going up. And then later, after member 4, filled up the cavity and choked it off, we had time and water was going into that cave, dissolving a little bit of the member 4 away and opening up some cavities. There was collapses locally. That opened up a little bit more space, and we had member 5, a younger member that came in. And you can see that as the orange deposits on this diagram. So member 5 came in on the top up there where you're circling. But then there were also little cavities dissolved inside member 4, like just below there. And we say it's intruded. So the member 5 is younger, but it's actually found inside the member 4. And this is tricky to recognize. It wasn't recognized for a long time at that site. But you can see in this diagram the sort of lateral extent of member 4. You can see the 2 of the places that we dated in green. And then you can also see flowstone in there. We just talked about stalactites and stalagmites, but you also get layers of flowstone, and those are shown in yellow. That's what was largely being blasted out and mined from this area, these thick layers of flowstone in what we call the breccia, the coarse sediment that has these pieces of the dolomitic limestone, sand and soil from the surface, and bones, and basically everything that fell in from the surface.
So when you say flowstone, is that sort of dissolved calcium carbonate that then sort of seeps in through the layers and then makes the stalactites, stalagmites that we see, or layers of similar features?
So yeah, flowstone is the generic term. It can refer to the stalactites and the stalagmites, or it can be basically anything deposited by dripping or flowing water in the cave. It dissolves calcite from the dolomitic limestone bedrock, and then percolates into the cave, and as it degasses carbon dioxide, it precipitates out the calcium carbonate mineral. And so that's accumulated as stalactites and stalagmites, but also it can accumulate inside the breccia. It can flow over surfaces. So if you're in a tourist cave, you'll see pretty layers of flowstone. There are lots of different forms that it can take.
It reminds me a little bit of the North York Moors up here in Yorkshire as well. We have a lot of these kind of caves and stalactites and stalagmite formations as well. So I'm quite familiar with these features. That brings me very nicely onto Daryl. That you mentioned a lot of things there. it seems incredibly difficult to work out exactly what's happened in this landscape. So how do we usually go about dating the fossils of hominins, and why is it so incredibly difficult in this case? Because when I was looking at the East African ones, and I think you mentioned it, you have things like volcanic layers where you can date them quite precisely, and these kind of things. But when we have a cave like at Fontaine, it seems a lot more difficult, and there's a hell of a lot of different things going on. So how do you go about trying to get the dates?
There are complications. So there's kind of two levels. Let's go back to East Africa, which is in many ways a lot simpler. You have lake basins that are accumulating sediments in sort of a layer cake fashion. They're later faulted and mixed up, but you can work out the stratigraphy, the order in which the rocks were laid down. And then there are volcanoes blasting off at the same time. And so there are layers of ash in there. And when a volcano erupts, you're forming new mineral crystals from the molten rock. And so we're able to date when those crystals formed by looking at radioactive products. So they have potassium in them, and potassium has a radioactive isotope that decays to argon. Being a noble gas, the argon is completely missing from these fresh minerals. So we can measure the buildup of argon and date those. Yeah. In the cave settings, the sedimentation isn't necessarily as straightforward, because you can have different rooms opening up at different times. You can have partial collapse of the sediments, cementation with calcium carbonate. You have to do very, very careful stratigraphy. That's something that Dominic has done with Laurent Bruxelles, who's been working at the cave for many years now. So we rely on a very careful stratigraphy. But now you've got to figure out, how do you date these things? Yeah. And there's a couple of traditional approaches. Well, I can think of three I'll talk about. One, and that's been around the longest, is just to look at the animals that fell in at the same time that are associated with these hominins, and then find similar animals in East Africa where we know how old they are. Yeah. So if you find, different antelopes, bovids, pigs, all of these animals are evolving at the same time. And if they're evolving at the same time in East Africa and South Africa, well, then you can correlate those two.
And we should make it clear for people, you can't do any sort of DNA dating, because the DNA is so
too far
old.
back, way too far back for the DNA dating. And for this to work, you have to be dead certain of your stratigraphy, but make sure your animals are coming from the right place, and we'll probably come back to that. Yeah. And you have to assume that the animals are evolving simultaneously across Africa. This is all relative dating. When you get, we can get to other methods that are closer to absolute dating. You can look at the magnetic field orientation. You can look at paleomagnetism. So the North Pole and the South Pole of the Earth flip back and forth over time because of the way that Earth's outer core is flowing, generating magnetic fields. It can just flip back and forth. And we can tell when a rock was laid down or when it was deposited, which direction was the North Pole facing. Yeah. And so that helps us to narrow down the time range through paleomagnetism. And this has been done at Fontaine, but only in those calcite layers where there's a good paleomagnetic signal. And then a third way you can do this is to try to date when the calcite deposited itself. So kind of like when we looked at the volcanoes, you have a new mineral forming, you get a new mineral of calcite forming, and that contains a little bit of uranium. So you can look at the daughter products of uranium, go all the way back down to lead, and use that to date when the calcite forms. The problem is, it gives you a very, very good age for when the calcite was deposited.
But I guess it's a liquid that can flow in between things and get... Yeah.
That's what I was pointing out on this last diagram is, what if the calcite actually formed inside the breccia instead of on the surface? Yeah. And that's what we believe happened here at Fontaine. I'm sure we'll come back to that. Yeah. And then, do you want to go into the dating method that we used here, or?
Yeah, for sure. Please do. So that was literally the next question I had is what was the process used to date the fossils in the new study? Because this as a particle physicist, it was very interesting to me as well.
Yes. So the method that we used uses cosmogenic nuclides, and I specialize in dating cave sediments and in these cosmogenic nuclides. What cosmogenic nuclides are, they are radioactive particles that are produced by cosmic rays coming in from space. So we have these super high energy particles accelerated by supernova explosions. They hit the top of the Earth's atmosphere, these primary cosmic rays. And like this diagram shows, they start a whole chain of nuclear reactions in the atmosphere. You get a secondary cosmic ray shower that propagates down. And they do things that you've probably heard of, like they'll change nitrogen into carbon-14. And this is the basis for radiocarbon dating. They also make other nuclides, radionuclides in the atmosphere, E6, all kinds of, beryllium-10 is made in the atmosphere. Most of the energy is absorbed in the atmosphere, but some of these particles make it all the way down to Earth's surface. These include muons that are made in the upper atmosphere, these short-lived but penetrative particles, and then a lot of secondary neutrons and a few protons. And those pass through rocks, and they have enough energy to break nuclei apart inside those mineral crystals. And so what we look at, we use the mineral quartz, which is very simple and very resistant to weathering. It's made of silicon and oxygen. And when it's hit by a cosmic ray, the silicon can break into aluminum with a mass 26. It's radioactive. It's got a half-life of about 700,000 years. And the oxygen can break into beryllium-10, basically make anything smaller by breaking the fragment off. Beryllium-10 is radioactive with a half-life of about 1.4 million years. So we have these two nuclides that are produced at the same time in this mineral crystal, but they have different half-lives. So the longer a rock is exposed at the ground surface, the higher the concentration of these two nuclides builds up. And we can tell how long a rock has been exposed at the surface. The key for this is that when the mineral crystal is buried in a cave, it's shielded from cosmic rays. We're buried 10 meters under solid rock, and that blocks most of the cosmic radiation. So if a rock was exposed first and built up concentration of these radionuclides, after it's buried, they both decay away over time at different rates. And we can use the ratio between nuclides to date how long ago it fell into the cave, back to about 5 or 6 million years.
Amazing.
So it's a completely different method than these others. It's not based on the formation of a new crystal, it's based on the burial of something that was previously exposed at the surface.
Amazing. What sort of assumptions go into that? I guess constant cosmic ray flux and sort of the idea that it fell under the ground and immediately stopped being exposed. Is there anything that any sort of uncertainties in that process that we should potentially be aware of?
So there are a number of uncertainties, right? Every dating method has uncertainty. Some of the assumptions that go into this, we assume that the sediment was exposed at the surface continuously, so that it wasn't previously buried. It didn't, spend 100,000 years at the surface, and it was buried a few meters deep, and then re-exposed, and then buried again. It needs to be continuous exposure, and the landscape is eroding, and then it's buried, and it's buried only once. That's the key assumption. So we do two types of dating here. We do what I call simple burial dating, where you just have one sample. That's all you got is one sample. And with one sample, it's really impossible to know if you had one burial episode or two. All you get is the total time that it's been buried. and this has been a criticism, it's a weakness of the dating method, because, okay, maybe it was buried twice. But we also use what's called Isochrone burial dating, where we have a bunch of samples that were all dated, that were all buried at exactly the same time. So they have exactly the same age, and they've had exactly the same post-burial history. And if they all line up and form a perfect line, and if that's consistent with, the burial depth that we see, then that gives us a lot of confidence in the result. Everything is working, and it's really, really hard to come up with a scenario where they all started with different concentrations, then they were all buried twice. It's just really hard to come up with.
Yeah, we're never 100% in science, but it makes sense, and it would be a very low probability of it not happening.
The isochrones are they give us a huge boost in confidence in these ages.
Makes sense. Dominic, I'll come to you then, because you haven't spoken for a while as well. So, what were the new findings when we put into effect this new dating method? How did they change the information that we had about these fossils previously?
So that's a good question, and I'll sort of talk a little bit about the previous method and what those conclusions were. So essentially, previously to these new dating methods, there was sort of one sort of major paper that suggested that the member 4 deposit dated to between about 2.6 million and 2.15 million. And that was based on dating of, as Daryl was talking about, the flowstones. So using radiometric techniques on the flowstones. So there was a flowstone that was identified that was at the bottom, proposed to be at the bottom of member 4, and then another flowstone that was proposed to be at the top of member 4. Sort of we can term a capping flowstone. So there's something that at the top and the bottom we call bounding flowstones. And so by dating the top and the bottom, these flowstone units, then the resultant date suggested that exactly. So the sandwich of sediment between them was between about 2.6 and about 2.15. And then, of course, everything that is within those sediments, the fossils as well, it's also within that sandwich of those flowstones. Through a great deal of stratigraphic work, and then a great deal of effort on Darryl's part with the sampling and the dating, we managed to reassess the integrity of those flowstones and the association of those flowstones to the sediments themselves. And we've already spoken about the potential of these flowstones to be sort of intrusive, so to work their way into an older deposit. And so at the lower flowstone, we correlated that with a unit that's actually exposed in a place called the fossil cavern, which you can see on the diagram. And we think that's likely to be an intrusive flowstone, something that's come after the actual deposit. On the top end, that sort of capping flowstone, some geological sort of mapping and some stratigraphic work shows that flowstone as well is not actually associated with the member 4 breccias and the hominins themselves. And so that sort of discounts that. And then through the stratigraphic work, we suggested that this lower flowstone is not associated with the sediments. And therefore, it provides an ideal opportunity for us to reassess the age of that deposit, because there's some questions there. One of the other big questions is that there's an interesting formation here between member 4 and member 5. And Daryl was responsible for sort of previous dating efforts on member 5, which put that deposit at about 2.18 million. So it'd be very strange to have the subsequent deposit, something that's supposedly younger, as being a little bit older than the deposit that's sitting over the top.
And that layer, it's important to say that layer has stone tools in it. It has artifacts, and there are no artifacts below. So it's certainly
they're very different. And there's clearly, when you look at the the contact between the two, there's clearly an erosion and a significant amount of time that's gone between the formation and then the end of the formation of member 4. And then there's been an unconformity or a long time where that member 4 has been essentially, bits have been taken away and it's been eroded and weathered. And then member 5 has come over the top. And so there's this really odd stratigraphic relationship that didn't really make sense with those dates.
Yeah.
And so through these new, the application of this cosmogenic nuclide burial dating on member 4, we now have a situation which provides a much more coherent stratigraphic sequence between what is member 4 and then 3.6 to 3.4. And then there's a quite a significant amount of time missing in the Sturk-Fontaine stratigraphic sequence. And we can account for that geologically. We see it in the deposits and the sediments. And then after that, 2.18 million years ago, then we get the introduction of the next deposit, which is quite different and contains different fossils and contains stone tools coming in afterwards. And so that makes more stratigraphic sense.
Yeah.
And then so this sort of these new dates essentially recalibrate member 4 to a point where we're now more confident that there's some kind of coherence between the geology and the dating. And I think if you asked and you looked at the biochronological, that is using the animals to date something like member 4, then if you look at those dating proposals, they could very well fit in within a 3 million year old deposit. It was actually only a couple of fossils that also have come into the deposit later through these sort of solution cavities, these holes that have opened up through the weathering of the deposit, where younger fossil was dropped in to a sort of in the little cavity itself within the older deposit, which then confused things because when people were, oh, hang on a second, I've found a fossil that actually belongs to something newer in these older sediments. And so a lot of our work in this paper was also going back and tracking any fossils that may be younger. We have to go find them and we have to figure out what they were and how
did they get in there?
Account for them. Exactly. Yeah. So the idea is that all of your evidence hopefully is supportive of itself. If you find something that's anomalous, then we have to go and find out why it is and what happened.
As a physicist, I can see why it's much easier to deal with layers of sediment or volcanic rock and crystals than human activity and weathering and things changing and geological activity. It makes it much more difficult. But as you say, I was going to ask, how can we be more confident that we've got the right answer this time? But it seems like all of the new findings line up nicely in terms of like you said, the sort of layers that we have, the stratigraphic work, also the fossils, and also with the dating as well. It all seems to make more sense in a kind of history of man chronological order, if that makes sense.
Yeah, I think it makes a lot more sense. And I'll just add the story of the horses. Like the last thing that we had to deal with is these supposed horse fossils that were found in member 4. And if our data is correct, there could not have been any horses. They did not exist in Africa at that time. So we had to go in and find every horse fossil. And there was one in particular that was deep in member 4. And then we found that one. It was classified as an ankle bone of a horse. And so for a long time, we were trying to figure out, okay, I never thought I would be that interested in horse ankles. Did it come from a modern one-toed horse, or did it come from an extinct three-toed horse? And it turns out it wasn't even a horse. It had been misclassified years ago and persisted in the record. And that was just like one of the final things, one of these final objections, like it couldn't be right. And then, but everything like that has fallen into place with these ages.
Amazing. So, that's just absolutely amazing. As soon as we start to see these lines of evidence all lining up in one way, we can give us much more confidence. So, is there still any serious pushback in the field, or anything else that needs to be sort of ironed out before people are happy with this? I've seen some comments in various articles that people want to see more blind studies and things like this. Is there any serious pushback within the field still on these datings?
there will be pushback. And I just want to address that particular comment to say that there have been blind studies where people run samples at different labs.
Yeah.
They'll send samples, and run them in my lab and someone else's lab, different AMS facilities. The published examples all are spot on. There's one unpublished that I think has an issue, but it's something that we do. It's something the community does. The AMS community intercalibrates all the time. So I thought that was a little bit of a maybe an uninformed comment.
When the media ask people for comments, maybe they go to people who are not involved with the work, and they make sort of generalized comments without.
But it's a fair comment, and it's something that is important in geochronology, right? You can't just trust one person. Yeah, absolutely.
No, it makes sense. We're always skeptical in science, as
you're
well aware.
Trained to be skeptics and pick apart our work and other people's work.
Exactly right. So Dominic, maybe if I come to you, so with these new findings, how does that, and it's kind of a nice circle back to where we started. If these current findings are accurate, how does that change our understanding of how humanity potentially evolved on the continent of Africa? I'll bring back the. I don't know how useful this diagram is, but I'll bring it back so we can we can chat through.
Yeah. Well, this diagram is useful because it does identify sort of some of the key players, the key hominins that we see on the landscape in East Africa and South Africa. So I think what's interesting, and we're sort of mentioning this recalibration of member 4, pushing that back to that sort of 3.4, 3.6 time period is really interesting because of essentially the kind of assemblage and the kind of hominins you find in member 4. So member 4, for as long as member 4 has essentially been excavated and people have been looking at the fossils, and that's basically 80 years, people have been discussing and arguing about the kinds of the diversity of the hominins. So the member 4 Stoke-Fontaine hominins are really interesting because there are lots of different shapes and sizes of something that's blanketed within Australopithecus. So some people have said, oh no, there's more than one morph, not really committing to saying, well, there might be multiple species. And then one of our sort of close colleagues, Professor Ron Clark, sort of committed and said, well, hang on a second, I think there's two different things, two different types of Australopithecus in member 4, and said, well, maybe one of them is Prometheus, and this is named after a species that Raymond Dart named in 1947. And then there's the sort of classic Australopithecus africanus. The interesting thing is not necessarily what we're calling these things, but that there is this diversity of morphology, that there is a sort of a range of different types of, or sort of shapes of Australopithecus at Stoke-Fontaine. And that's really interesting because when we take these Australopithecines and look at them, different parts of them, different parts of those may hint at sort of an ancestral place or an ancestral sort of role in later hominins. So whether that's Homo, whether that's something like Paranthropus, is really interesting because we don't really know much about the origin of either of those genera. And they're really, really quite exciting in terms of what they turn into. And obviously, Homo turns into us, and Paranthropus goes extinct, but as a species itself, it's quite bizarre. We don't really know much about the origin of those things. And previously, when member 4 was dated to that 2.15 to about 2.6 date, essentially that was too early, that was too late. That said, well, hang on, Homo and Paranthropus both appeared before the end of member 4. So the likelihood of member 4 having, and the hominins in there, having any real input or ancestral relationship to those hominins is very, very slight, if any. So when you take those hominins and you sort of push them back to maybe that 3.6 to 3.4, you all of a sudden create a bit of a gap. And you say, well, after that period, between there's a good chunk of time between 3.4 and 2.8 or 2.6 when we see the earliest appearance of Homo and Paranthropus respectively. And then it says, well, hang on a second, these interesting features that we see in the member 4 hominins, maybe they actually are ancestral to maybe Homo or maybe Paranthropus. And these observations are not our observations. These observations have been made by other specialists over a long period of time and said, well, there's an affinity here between an Australopithecus at Stratford and Paranthropus, but the dates didn't quite fit and didn't allow that sort of time period, that gap for the evolution of those species. And so I think for me that's really exciting. On the sort of the negative side, I suppose it's not really negative from my perspective, we've created at Stoke-Fontaine this big gap in the stratigraphic sequence between member 4 and member 5. So there's a million years of time, or 1.2 million years missing. However, in creating and recalibrating Australopithecus, we've got an opportunity to explore how those may have influenced the evolution of Homo and Paranthropus in Africa.
So if we look at this diagram, we're basically taking the Australopithecus africanus, when I can say it, and sort of pushing it back in time, where it could have been even sort of a sister species with Afarensis as well. So instead of them having this Afarensis coming down as a common ancestor to these species or these hominins that you mentioned, you could now be pushing this back, and you have a common ancestor of both of them. So the tree is completely changed. Is that fair?
Certainly, I think the tree changes quite often. Certainly, there are often some new calibrations for dates, and so that the tree shuffles around, which is absolutely fair enough. That's what science is. Yeah. There's always a refinement of theories and hypotheses, and so you're absolutely right there. If you take Australopithecus africanus and what Ron has called Australopithecus prometheus, and if you push those back to a point where they're coeval or existed at potentially the same time as Afarensis, then you've got a few contenders. Then we say, well, hang on a second, where do we find Homo? Where might it have evolved? Where do we find Paranthropus? Where might that have evolved? And then also, what's going on between Afarensis and the Australopithecus africanus? And what was their ancestor? And so I think it just provides some more questions. And those questions, instead of necessarily sort of pushing aside the Southern African Australopithecines and saying, well, hang on a second, that's sort of an area in Southern Africa. It doesn't really relate much to what happened in the greater scheme of things. Now I think there's an opportunity for us to ask questions about Australopithecus in South Africa.
Very, very interesting. Does it open up a possibility that, well, I guess it must do, that common ancestor evolved elsewhere on the continent of Africa, potentially in South Africa or East Africa, or even somewhere else that we haven't seen yet?
I think, given that we have a very fragmentary fossil record, given that our sampling of that fossil record is extremely biased geographically and geologically, I think it's misleading to say things like cradle of humankind or cradle of mankind. That is just where we find the fossils and they've been preserved. And so there is undoubtedly evolution happening in the rest of the continent. And I suppose it's quite nicely demonstrated when in Morocco a few years ago, then we had an earliest member of our own species, Homo sapiens, appeared. And that was sort of out of the blue, essentially, because everyone had sampling mostly in East Africa and South Africa, and then this thing appears in Morocco at 300,000. We're like, well, hang on a second. There's undoubtedly evolutionary changes and hominins changing in the rest of the continent as well.
That brings me on to my final question then. So, where would we, for both of you, this question is, where would you like to see more data taken? What sort of things would you like to be undertaken to get us a better picture of this evolutionary tree? Because as you say, at the moment it's kind of looking at a jigsaw with most of the puzzle pieces missing, probably. What sort of analysis would we and sort of studies would we need to do to get more information about this? I guess it's looking for more fossils in the first instance. Is that fair? Come to Dominic first, and then Daryl to round us off.
Yes, it is finding more fossils. It is being able to accurately date those deposits. There are areas that are geologically sort of quite interesting and may provide opportunities to find ancient deposits. And it's about essentially surveying and doing the very heavy groundwork of walking the field to see if you can find these things. And there are some really interesting areas, the sort of northern Mozambique, where you find the southern part of the Rift Valley. And also, geologically, you find caves and karst landscapes. And so that's quite interesting in the merging of the two sort of sediment trap types. And it's about essentially getting into these areas and doing the survey work and having the support to be able to date those things as well. Hominin fossils are extremely rare. And so it's not that these things appear in every cave that we look in. Yeah. So it does take a massive investment in time, money, and manpower to really find these things.
Right. You got to be lucky at the same time.
Yeah.
Daryl, anything you'd like to add to that?
I think that what we see in South Africa, looking more locally, is, when we're revising the chronology here, this is, I think, going to open up some questions about the relative ages of different sites in South Africa. So recognizing now the age of the fauna of the animals that were associated with Sterkfontein may open up some reevaluations of some of the other sites in Cradle to Mount. I think that's going to be really interesting to watch as that shakes out, because we've thrown things back a million years, but also identified a few of these outliers that were younger and mixed in with the older deposits, and that changes the faunal assemblage.
Are there any openings for using the cosmogenic analysis for other findings that have already been dated, and potentially either verifying those or maybe changing them?
I think it's worth looking at more closely, very closely. Many of the other sites are not as deeply buried. The stratigraphy may not be as well mapped, a bit more controversial. Some of the sites are more surface accumulation sites, but it's worth, I think, trying and exploring a little bit more than we have, actually. So something we can talk about offline.
Yeah, definitely. It's really, really, really fascinating stuff. Thank you very much to both of you for going through that with me. It's so interesting. Just as we sort of come to an end, is there anywhere where you'd like to sort of point people to find out more about this? I'll make sure the paper is posted in the comments below, along with both of your kind of work and socials. Is there anywhere else you'd like to point people to find out more about this work and what both of you are doing?
Daryl?
I'll start with Dominic.
Yeah, so the Sterkfontein Caves has a sort of a Facebook site as Sterkfontein Research, which we give sort of fairly regular updates when I can get out the caves and get out the lecture hall. Then yeah, so that provides
when the power's working in South Africa as well, apparently.
That too, yeah. So that provides sort of some regular updates in a very sort of informal way as to the general research directions and what our activities really. And in terms of this research, then Darryl's and Purdue have set up some nice resources to understand better this research.
Yeah, and in terms of the dating methods, we have Prime Lab here at Purdue, the Purdue Rare Isotope Measurement Laboratory. It's an accelerator mass spectrometer, and people can learn about the dating methods there. And we should have, if they're updated, links to several papers about the basics of the dating methods.
I definitely want to work up maybe a kind of documentary style video on this, because it's very nice with I really like the interplay of the kind of field work that's going on with the sort of hard science and sort of particle physics that's going on behind there.
Yes, it's a mix of particle physics.
Yeah, exactly.
And
That's what I want to be, sort of, the Indiana Jones style particle physicist would be, a nice mix of the two. Amazing. I will make sure all those links are down in the description. I know Dominic needs to run off now. Dominic, what have you got planned this afternoon?
This evening, it's a sort of an award ceremony. I'm not getting an award, but I'm going to an award ceremony that's sort of celebrating South Africa's young and upcoming scientists.
Oh, amazing.
It'll be fun.
Awesome. Daryl, yourself?
Yeah.
I'm just in the lab.
back to the lab, working stuff out. Yep. Awesome. Well, I will thank you both again. Thank you so much for taking the time. And hopefully the next time we get some clarification on this, we can get you guys back and we'll have another wonderful chat.
All right. Thank you.
Thank you very much. I will talk to you both soon. Thank you very much.
Perfect.
Have a wonderful evening.
Cheers. Bye-bye.
Bye. Bye.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.